Hello, welcome back to another day, another adventure. And we are going to talk about chemistry today. So let's start with a couple of questions. And question one would be, can you explain what atoms are and how they relate to molecules and compounds? So atoms are basic building blocks of matter, often visualized as billiard balls, so just circular things. And molecules would form when two or more atoms bond together. And compounds are substances made up of more than one type of atom bonded together. And the basic unit of compound is a molecule. So atoms are the basic building blocks. Molecules form molecules form when, like, if you have atoms plus atom plus atom, or a lot more atoms, that's a molecule. And then if you have a lot of molecules, more than one type of atom, wait, one more, compounds are substances made up of more than one type of atom bonded together. So that's the difference. Molecules are when two or more atoms are bound together, while compounds are when, like, different types of atoms are bonded together. And how do atoms and molecule play a role in chemistry as the middle science? Well, it would bridge biology and physics, focusing on the real world substances like the atoms and molecules. And you can see how matter would behave at the molecular level for that. And what's the difference between elements and compounds? And can you provide examples of each? So the difference with them between them would be elements consist of only one type of atom. Meanwhile, examples of those would be gold, oxygen, and iron. And meanwhile, compounds would be different types of atoms together, like water, H2O, and carbon dioxide, CO2. And how is atomic size measured? And what's the typical order of the atomic radii or radii? So atomic size is measured usually in nanometers, and the order of an atomic radii or radii is approximately 0.1 nanometer. So the atomic size is measured using nanometer. And other units used for it is angstroms, the A with fancy O at the top, and picometers, PM. And an angstrom would be 10 raised to negative 10 centimeter, and the picometer is 10 raised to negative 12 meters. Okay, how can we describe an ionic bond and provide an example of where this bond occurs? An ionic bond is when one atom completely transfers an electron to another atom. So again, ionic bond is when an atom completely transfers an electron to another atom. And this will result in oppositely charged ions that are held together by electrostatic charges or forces. Again, atoms are the building blocks. Molecules are formed when it's like two or more atoms together. Compounds are more than one type of atom bounded together. Elements are the same types. Angstrom, 10 raised to negative 10 cm. And next is ionic bond is when you transfer an electron from one atom to the other. Opposite charged ions are held together by electrostatic forces. Example would be NaCl, sodium chloride. Sodium loses an electron to chlorine, and you form Na plus and Cl minus together. And they attract each other. Okay? What's the difference between ionic and covalent bonds? Ionic and covalent bonds. Well, ionic, again, transfers electrons from one to the other. And the covalent bonds would be sharing. Covalent sharing. Covalent, that is sharing. You just let it borrow. Oh, it's witty. That's very witty. Hello, thank you. Yeah, so covalent is sharing. Meanwhile, how does the process of glycolysis contribute to ATP production, and why is it important in the absence of oxygen? So glycolysis is the anaerobic breakdown of glucose into pyruvic acid. And that produces a small amount of ATP. Again, glycolysis is the anaerobic breakdown of glucose into pyruvic acid, and that would produce a small amount of ATP. And in the absence of oxygen, aka no oxygen, that's why it's anaerobic, it would allow cells to generate energy even when oxidative processes like the ETC or electron transport chain cannot function due to the lack of it. And glycolysis also produces NADH, which can be used later on in the oxidative processes if oxygen is now available. But if there isn't, you have glycolysis, which is, what is it? Breakdown of glucose into pyruvic acid. There's a lot of steps. I'll talk about that later. And what's the role of acetyl-CoA in cellular respiration, and how is it formed? So acetyl-CoA is a key molecule in cellular respiration. Acetyl-CoA is formed from pyruvic acid after glycolysis. So you have glycolysis, which is from the glucose into pyruvic acid, and from pyruvic acid, at some point you make acetyl-CoA. It enters the Krebs cycle. It is further oxidized, which ends up producing NADH and FADH2. NADH and FADH2 would be used in the ETC to generate ATP. Guess what is that? That's the primary energy source for the cell. And how does the electron transport chain contribute to ATP production? ETC is the final step in glucose metabolism, and it occurs where? Where does the ETC occur? In the inner mitochondrial membrane. Where does the ETC happen? It's in the inner mitochondrial membrane. And NADH and FADH2 is generated in the earlier stages. They will donate their electrons to the ETC, and you have a proton gradient now across the membrane that would drive the production of ATP. Why? Because you have the ATP synthase, which uses the flow of protons to generate ATP. If we want to measure the oxidation of ethanol, what enzyme should we focus on, and what's the product? We want to focus on ADH, alcohol dehydrogenase, and that would catalyze the oxidation of ethanol into acetaldehyde. Again, if we were to measure the oxidation of ethanol, which enzyme would be focused on, and what would you expect as the product? Focus on ADH because that would lead to the oxidation of ethanol into acetaldehyde. And this would also involve the reduction of NAD plus to NADH, and the product of this reaction is what? Acetaldehyde. It's then converted into acetic acid. So acetaldehyde into acetic acid by what? Acetaldehyde dehydrogenase. So again, ethanol into acetaldehyde, you have alcohol dehydrogenase is the magic syrup in there. You also have NAD plus being reduced to NADH, and then acetaldehyde is then converted into acetic acid via using acetaldehyde dehydrogenase. Okay. How would we, where's my sticky note? Here. How would you address a case of methanol poisoning in an experimental or clinical setting? Methanol poisoning would occur when methanol is metabolized to formaldehyde and then to formic acid. So methanol, formaldehyde, formic acid. So to treat this, fomepizole, an alcohol dehydrogenase inhibitor, would be able to block the conversion of methanol into its toxic friends. Ethanol can also be used to compete with methanol, and then you can prevent the buildup of toxic metabolites. So that's why in labs you would want to use ethanol instead of methanol Again, if you have methanol poisoning, it's because methanol can be metabolized into formaldehyde. You know those crime shows that you watch. You must have encountered that one. Formaldehyde into formic acid. So use omeprazole and an alcohol dehydrogenase inhibitor to fix that. Okay. So again, atoms, billiard balls, molecules, two or more atoms bounded together. Chemistry is the middle science between biology and physics, studying real-world substances. Elements is only an atoms of only one type. Compounds is more than one type. Atomic size nanometers, 0.1. Metals versus metal packing structures. Metals are, you have like gold. Most elements are metals, like gold, iron, magnesium, copper. You have gaseous elements and such as hydrogen, H2, nitrogen, N2, and oxygen, O2, and chlorine, Cl2. And on to study the nature of chemical bonds, you have to understand the atomic and molecular structure. You have the nucleus. It consists of protons and neutrons, and it contains most of the atom's mass. Hello. I know. I'm trying to. Hi, great teacher. I'm trying to find a way to write and to have a board. Yeah, next time. I'll figure out how to draw, hopefully. Okay, so we have the electrons are distributed into orbitals of different energies, and you call them as orbitals rather than orbits due to quantum mechanics. That's a different topic. And these orbitals would represent electron clouds that are indeterminate in space, with their exact position being uncertain. Yeah. I know. Yeah, no whiteboard. No. I don't know how yet. Is this like you just share the PowerPoint and then you scribble on it? Hopefully an iPad would be able to connect. Any suggestions? I would love that one. So that we have visuals and diagrams. Chemical bonds, almost all of which depend on electrons, and they can be broken down into ionic bonds and covalent bonds. Ionic bonds, complete transfer. Covalent bond is lending, just share. And electromagnetic force would play a key role in these bonds, and it is the only force involved in chemical bonding, and it operates through attraction between oppositely charged particles. And this force is attractive between substances with opposite charges and repulsive between charges. So, it's likes repel, right? It's the minus and plus. Those would repel, but the minus and plus would like attract. Likes repel, opposites attract. That's the thing. Electron shells, the also of electron shells, it's an important concept in understanding chemical blocks. The first few shells contain electrons, and the distribution of these electrons in the outermost shell is very critical in MS Paint. Oh gosh, using the mouse to draw the orbitals, crazy. Yeah, that would be funny. These concepts and processes are explained using principles from quantum mechanics, so just different electron shells. You also have the trends, elemental trends, and it's like the same groups. The periodic table groups elements based on their electron configuration, with elements in the same group having similar chemical properties. Group 1 would have a single electron in their outer shell, and that's why they're highly reactive and most likely will form cations. And you have water. Okay, water. It's a molecule with polar covalent bonds between hydrogen and oxygen, and it is one of the most common examples used in chemistry. The oxygen atom would pull the shared electrons together, making it slightly negative, while hydrogen is slightly positive. That's why water has its high boiling points and solvent abilities because of hydrogen and oxygen. You also have carbon. Carbon plays a key role due to its ability to form carbon-carbon chains. It's the simplest organic molecule, CH4 or methane, would demonstrate the fundamental carbon-hydrogen bond where the carbon would share its bonds with four other hydrogen atoms. And you have, yeah, CH4. You also have four fundamental forces that govern the interactions in nature. You have the electromagnetic force, gravitational force, strong nuclear force, and weak nuclear force. Electromagnetic force would be the force responsible for the interaction between the electrically charged particles, and it's the most relevant force in chemistry. The electromagnetic force. Gravitational force would be for large-scale interactions in the universe, such as the planets and stars, but it is too weak at the atomic scale to affect the behavior of atoms and molecules significantly. You also have the strong nuclear force. It holds the protons and neutrons together in the absence of an atom. It's very strong, but it can only act over short distances. Okay? And within the nucleus itself as well. Weak nuclear force, that is for the radioactive decay. Okay, now let's try and talk about some like polar bonds. So again, chemical bond would be the attractive force that holds together atoms in in a molecule. Valent bond is where it is shared. An even distribution of electrons would lead to polar covalent bonds, but the bond can also be non-polar, where it is shared evenly. So a covalent bond can be polar or non-polar. Polar is where electrons are shared a little bit more on one side, while non-polar is more even, an even distribution. And to determine if it is polar or non-polar, you check the electronegativity. What is electronegativity? It is the tendency of an atom to attract electrons in a chemical bond. Again, electronegativity is the tendency of an atom to attract electrons in a chemical bond. And atoms with higher electronegativity will attract electrons more. So if you're more electronegative, you attract electrons more. Thus, you have a more polar bond. And that will classify it as being ionic or covalent. Ionic is just a very large difference in electronegativity, while covalent would be a smaller, moderate difference. Okay. That one's finished. Ionic bonds. Dipole. Okay, the type of, let's go with types of intermolecular bonds. You have dipole, and hydrogen bonds, and van der Waals. Okay, so dipole, permanent dipoles that occurs between molecules with permanent dipoles. Positive end of the molecule of one molecule is attracted to the negative end of another one, creating a bond. And these interactions are particularly important in polar molecules like HCl. The very negative side, being attracted to the very positive side, boom. You also have hydrogen bonds. That's a dipole-dipole, and a special case of dipole-dipole. It's when a hydrogen atom is covalently bonded to an electronegative atom, like oxygen and nitrogen. And they're very key structures in like water and other biological molecules. Also, the van der Waals forces kind of weak. They're weaker forces due to instantaneous dipoles in molecules, and electrons move randomly, creating temporary dipoles, and those would induce dipoles in neighboring molecules. Hydrophobic interactions. What's that? Now we are in the properties and effects side. So it occurs when non-polar molecules would aggregate to minimize their contact with water, which is energetically unfavorable. And this is a phenomenon in protein folding, especially during lipids. We'll talk about that later. Because, for example, the hydrophobic side will want to stay inside and not interact with the outside section. All right. You also have organic, a little bit of organic chemistry, but we can we can talk about it a little bit. All right. Let's So organic chemistry focuses on compounds with carbon-based structures, and every organic compound contains two parts, a hydrocarbon backbone and a non-hydrocarbon part containing functional groups. And these functional groups are reactive portions of the molecules, and they determine their chemical properties. Okay, that's organic chemistry now. Hydrocarbons are molecules made up entirely of carbon and hydrogen atoms. That's why it's hydrocarbon, and it's a backbone of many, many organic compounds. That's where you get your alkanes like the methane, ethane, propane, butane. It is CH something something. And it could be linear or branched. So methane is CH4, it's met it's prop, but, and then the rest would follow the numbers like pent, hex, and hept, oct, non, and dec. Methane, ethane. So let's start. Methane is CH4. Ethane is C2H6. Propane, guess what? C3H8. Butane, C4H10. Pentane, pent, C5H12. Hexane is C6H14, heptane C7H16, octane C8H18, nonane is C9H20, decane is C10H22. Okay, and you have different formulas, such as for cycloalkanes, you could have the molecular formula. Example, you have cyclopropane, that's the triangle looking one, C3H6. You have 3 carbons, and then you draw a line in the middle of each one, so you have a triangle. The H2s are beside them, and then you have a line formula, just a triangle. And then the presence of functional groups such as like alcohols, aldehydes, and other fatty acids would add to the reactivity of these hydrocarbons. For example, alcohols would have an OH group, and they can form through the reaction of an alkane like an ethane with an OH. So ethane, ethanol. Propane, propanol. Butane, butanol. Okay. And then you also, this is just a special part, like cholesterol. So you also have an OH group at the end. Aldehydes have carbonyl groups like C double bond O, and it is formed when an alcohol is oxidized. So an aldehyde, C double bond O, and then an H at the side, happens when an alcohol is oxidized. Example would be ethanol turning into acetaldehyde. Fatty acids such as oils would contain the COOH carboxyl groups, where the acid functional group is responsible for their reactivity. And then you have simple organic compounds such as hydrocarbon chains forming the simple stuff such as the methane, ethane, and propane. Intermolecular bonds, we talked about that. Oh, carboxylic acids, you have COOH, and it's always numbered 1. The carboxyl group is always 1 when naming it with the IUPAC, IUPAC. Longest chain is identified, and you add the ic acid. It's added to the name of the compound. Example would be acetic acid. It's commonly known as vinegar. It might be in your kitchen, especially if you do adobo. Yeah. Okay, the structure of acetic acid can be represented in several forms, such as the Lewis structure, 3D configuration, and its structural formula. So it's always carbon number 1. If you find the longest chain, drop the E, add oic acid, and that's why it's now called ethanoic acid. Some example would be formic acid, which is found in ants, acetic acid, vinegar, propionic acid. It's found in milk. So, butyric acid, it's found in butter. Valeric acid, it's found in valerian root. Caproic acid, it's found in goats. Enanthic acid, it's found in vines. Caprylic acid, it's found in goats again. So much oats. Pelargonic acid, it's also non-anoic acid. It's found in an herb. And capric acid, found in goats again, that's the decanoic acid. So yeah, formic acid is methanoic acid. Acetic is ethanoic acid again. Propanoic acid is just propanoic acid. Prop but. You have benzene derivatives, such, for example, you have 2-amino 3-phenyl propanoic acid. It's derived from propane. It has COOH and a phenyl group as a substituent. And you have some more complex naming schemes. So, for example, you have 3-hexanol. Yeah, that's a 6-carbon chain. And you have an OH at its position 3. So that's why it's 3-hexanol. 3-hexanol. There. It's a hexane with an ol at the 3. So same goes for 3-octanol. It's an octane with a hydroxyl group on carbon 3. And then you have things like 6-ethyl 4,5-dimethyl 3-octanol. That's a wrap. So you have an S6. So it's an octane. Look at the endpoint. Again, 6-ethyl 4,5-dimethyl 3-octanol. Okay? The longest chain is an octane. The functional group is an OH. You have at the 3 part, you have an OH there, carbon number 3. And then you have 6-ethyl. So that means at the 6th carbon, you have an ethyl. You put 2 CHs there. Meanwhile, at 4-5, it says 4,5-dimethyl. So at 4 and 5, put methyls. So that's how it is. It may look complicated, but it actually looks pretty like a tree branch. Okay, and then you have carbohydrates would be essential molecules. But so far for the mini intro, I think that's good to go. All right. Thank you for watching. Bye bye.